Yeah, welcome back after the short break, and we are about to start the small signal equivalent circuit for the common source amplifier. And what we have said is that in the small signal equivalent circuit, first thing is that we are making the DC bias to be 0, and then the capacitor we have sorted here and the capacitor we have sorted here, and then DC current in this voltage dependent current source we made it 0, leaving behind the small signal current small IDS, which is linear function of the GS VGS here. So, the VGS is given here, and this is a linear function. So, the linearity is defined by this GM. So, the expression of the IDS, it is given here. This part is the GM, as I was telling before, or we can have another expression of the GM here. So, that is the expression of the GM, and then whatever the output we are observing here, that is the small signal output. So, just to highlight that the signal here, it is not having any DC, it is having 0 here, and whatever you are observing at the output, that is also having DC equals to 0. So, at the output we do have only the signal part. And if you see this circuit and if you try to analyze this circuit quickly, what we are getting, let me write the expression of this V out. It is V out equals to this, whatever the drop across this resistance you are getting, the current is flowing from drain to source. So, the output voltage, it is minus RD into IDS, and that is giving us minus RD into GM into VGS, and the VGS, it is incidentally same as Vs. So, that is equal to minus RD into GM into Vs. So, that gives us the voltage gain AV defined as V out, small signal V out by the primary input Vs equals to minus RD into GM. So, this is the first parameter of the voltage amplifier, namely the voltage gain. The second parameter, it is the output resistance. So, if you look into this circuit and then if you observe this circuit from outside, and if you see what is the corresponding output resistance. So, while we will be doing this, as we said that we can connect a signal source here, and then we have to make this part equals to 0. So, once you make this is equal to 0, this part it is 0. So, that makes this current, it is also 0. And then if you stimulate this output port by say Vx, and then if you observe the corresponding current here as Ix, in fact, the current, it is only going through this resistance. So, then Vx and the Ix relationship you will get is basically Vx is equal to Rd into Ix. So, that gives us the expression of V out, which is defined as Vx by Ix equals to Rd. So, that is the second parameter we obtain. Now, the third parameter, it is so at the input port, if you see, and if you see what is the corresponding resistance here, and since the circuit here it is open, namely the gate current is 0, whether it is large signal or small signal, as long as we are not considering the effect of the capacitance from gate to source, we can assume that this is equal to 0. So, if we again stimulate this port by say V s, and whatever the current we observe, let us say that this is I s, and this I s incidentally it is the current flowing through this R 1 and R 2. In other words, we can say that I s multiplied by R 1 parallel R 2, because this is connected to AC ground, this is anyway it is ground. So, that is why that makes this R 1 and R 2 coming parallel, while this I s current is flowing. So, I s multiplied by this parallel connection, that gives us the voltage there, which is V s, or we can say that I s equals to V s divided by parallel connection of this one, but whatever it is, that gives us the expression of I in, this will be I in, that is what I mean, I in equals to V s divided by I s. So, that is equal to R 1 in parallel with R 2. So, what we obtain here, it is A V, expression of A V equals to minus G m into R d, R in equals to R 1 parallel R 2, it is coming from the bias circuit, and then output resistance equal to R d. So, that is how the entire circuit you can map into this voltage model. So, and the of course, the expression of the G m, it is given here, either here or here. So, as a result, what we are getting there, it is once we map the circuit into a voltage amplifier, what we are going to get here, it is we do have R in, then A V. So, this is A V times, so this side plus and this is minus, A V times V in, where V in, it is the voltage across the input port, and then at the output we do have the Thevenin equivalent output port resistance R O. So, that is the voltage model, and we already obtained the expression of A V, R O and R in. And then of course, from outside, if we are giving a stimulus, say V s, and then if you are connecting some load here, then you can find the corresponding primary input to primary output voltage. Okay. Now, as we have given a hint that since in the main circuit this current, it is this I G s equals to 0 before we start considering the input capacitance. So, we can say that the signal at this input port, it will be always in the form of voltage. On the other hand, the output port, at the output port, the signal either can be voltage as we are showing here, but then it can be even current also. Yeah, I have a call now. I am going to restart. Yeah. So, what we are discussing here, it is the signal at this point, it can be either voltage, and then we call it as voltage amplifier, or it can be current. So, or it can be current, and if it is current, then the corresponding amplifier, it will be called transconductance amplifier. And what may be the corresponding model? At the input it remains the same, namely R in, but at the output we will be having a different model. This is Gm into V in. Note that this Gm, it is incidentally it may be same as the small Gm, that is the transconductance of the device, but in general need not be the same. And at the output side, we do have the Norton equivalent resistance or say conductance, output conductance G0, which is equal to 1 by R0. Now, these two circuits, of course, they are equivalent. So, this R in and this R in, they are same, whereas this Gm and this AV must be having some relationship, so that this circuit and this circuit, they are equivalent, namely this Thevenin equivalent signal source need to be converted into Norton equivalent source here. So, this G naught relationship of G naught and R naught, it is already given here. On the other hand, whenever the circuit is open, we are getting the voltage here the same as the internal voltage, which means that AV into V in, that must be same as whatever the voltage it is getting developed here, namely this should be equal to minus Gm into G into R naught. So, that gives us expression of Gm equals to Gm into V in into this one. So, let me rewrite this part somewhere here. So, AV into V in, so that is the open loop open output voltage. So, that should be equals to Gm into V in into RO with a minus sign. So, that gives us the expression or the relationship between this Gm and this AV. So, Gm equals to AV by R naught, and of course, with a minus sign here. And what we have seen that AV, it is minus Gm into Rd, and RO, it was Rd. AV is the minus sign. So, we do have one minus sign here, and then also you do have one more minus sign here. So, that gives us Gm of the device. So, incidentally, as I said that incidentally this Gm, it is same as this Gm of the transistor, of the MOS transistor, but in general it need not be. So, that is how the amplifier, there is a small mistake, this should be common source amplifier. So, there is the common source amplifier. So, that is how common source amplifier we can either map into a voltage amplifier, which is given here, or it can be mapped into this transconductance amplifier. Now, if we consider the high frequency situation, namely if we consider the signal you are feeding here, it is in the high frequency range, then we need to consider parasitic capacitances here, gate to source and then gate to drain capacitances. And if you want to also include the effect of lambda, then at the output side it may be having finite conductance. So, we may have to include the output conductance also, which is defined as which is denoted as RO and defined as change in IDS with respect to change in VDS. So, if you see the corresponding model, so what we will be getting there, it is yeah. So, this is the high frequency model. We can see that if we consider the device parasitics, what are the components we do have? It is we do have the gate to source capacitance. This is the gate terminal, and then this is the source terminal, and this is the drain. So, gate to source, we do have one capacitance internally, and that is coming from basically the this. If you recall the MOS structure, it is simplified cross sectional view, and this is where we do have the thin oxide, and here we may be having the channel. So, the CGS is primarily due to this capacitance. So, this is source and this is gate terminal and this is the drain terminal. So, CGS is this capacitance, which is Cox, capacitance per unit top view, multiplied by W into L. And since it is in saturation, you need to consider one factor 2/3. And on the other hand, if the device it is in saturation region, we can say that the whatever the fringe capacitance will be there, that is primarily contributing the CGD. So, there may be some fringe or overlap capacitance, and that capacitance is proportional with W. So, this is something called another parameter called C overlap multiplied by W, and typically this is much smaller than CGS. So, I should say magnitude wise this is dominating individually over this CGD. However, this CGD it is at this end it is not AC ground, rather it is having a signal. So, in case if we are thinking of as the small signal capacitance, and if we translate this this capacitance into an equivalent capacitance from input port to ground, then we need to consider Miller effect. So, the effect of this part CGD at the input port it may be translated as equivalent another capacitance, and this is due to this CGD, and it is equals to 1 plus this gain of the voltage gain of this circuit into this, I should say magnitude wise, CGD. So, we will be discussing this again later, but this is coming from the Miller's theorem, and it is referred as Miller affected capacitance. In addition to that, we are considering this RD, drain to source resistance, RD or RDS, and this is coming due to IDS is having some dependency on VDS. So, if I say that change in IDS with respect to VDS, so that is the output conductance, or we can say 1 by output resistance. And the expression here it is typically it is approximately rather this is equal to lambda into IDS. So, that gives us this is equal to 1 by lambda into IDS. So, this model, as I said, this model, it is giving us the high frequency model, and whenever we will be talking about frequency response of the circuit, in the mid frequency region we may ignore these two parts, and whatever the in case if it is a resistive load, then we may ignore this part, and then we may get the mid frequency gain. But if you go to say higher and lower frequency, depending on the coupling capacitance here and depending on the resistance here, we may be having the lower cutoff frequency defined by this C1 and R1 parallel R2. So, this lower cutoff frequency, it is 1 by 2 pi this R1 parallel R2 into the input capacitance, and input capacitance is CGS plus the effect of the CGD, which is 1 plus AV times CGD sorry, I will take it back. I will take it back. So, the lower cutoff frequency, it is defined by, okay, let me rewrite here. So far we are talking about the high frequency effect and the low frequency effect. So, as a result, the previous analysis, it was valid in the mid frequency region, and if you go to lower and lower frequency, the lower cutoff frequency, it will be defined by f cutoff low equals to 1 by 2 pi R1 parallel R2 into C1, where C1 it is the signal coupling capacitor C1. On the other hand, whenever we are going to higher and higher frequency, we will be having upper cutoff frequency here, and that cutoff frequency, it will be upper cutoff frequency U here. So, that is 1 by 2 pi R O and then C L. C L we are assuming that to be coming from the next stage or maybe whatever the load we do have. And in case if we have the signal source having a source resistance, say R S, and then in the high frequency, the upper cutoff frequency may be having one more possible candidate to define this upper cutoff frequency, in case if we have this R S, and then if cutoff frequency upper cutoff frequency in presence of this R S, it is 1 by 2 pi into R S into the input capacitance C in, and then C in it is having, so this C in it is having two part, one is CGS, another part is contribution from the CGD. So, this R S multiplied by CGS plus Miller affected part of the CGD, namely 1 plus magnitude of AV into CGD. So, that is the input capacitance. So, based on the magnitude here of this one, if I call say this is f upper cutoff frequency 1 and this is f upper cutoff frequency 2, then whichever is minimum we have to consider either this one or this one. So, that is the role of this CGS and CGD in the frequency response, and for high frequency analysis, we must consider these two capacitors. And on the other hand, R d, in case if you consider the output resistance here, including this R d, then the output resistance R o, it will be R d coming in parallel with small r d. And the gain, on the other hand, the voltage gain, it will be minus G m into this total resistance, which is R capital D in parallel with small r d. Okay. Now, so we have discussed about the mapping to small signal equivalent circuit and then biasing and all, more from the analysis point of view. So, let me cover one numerical problem. I think I do have I do have separate slide for that. Yes. The same circuit here we are considering, and also we have been given this parameters that k into W by L equals to 1 milliampere per volt, suppose it is given to us, and then threshold voltage of the transistor is say 1 volt. And on the other hand, the DC parameters, or rather bias circuit information, it is given as that VDD it is say 12 volt, and then R1 it is so 9 k, and R2 it is 3 k. So, how do you then find the gain? How do you find the gain of the circuit? And from this information, so what will be the procedure or sequence of calculation? First thing is the DC operating point, and to do that we need to get the DC voltage at the gate or gate to source. So, if you consider this R1 and R2 value, and then this is VDD equals to 12 volt, what we are getting is VG equals to VDD into R2 divided by R1 plus R2. So, that gives us 12 into 3 divided by 9 plus 3. So, that gives us 3 volt. In fact, this is same as VGS. So, VGS is equal to 3 volt here. Now, using this information, I can say that IDS, which is K W by L and also 2 in the denominator, VGS minus VTH square. So, that gives us K into W by L, it is 1 milliampere by 2, then 3 volt is the VGS minus VTH square. So, that gives us 2 milliampere of quiescent current IDS. So, the quiescent current flowing through this circuit IDS, it is 2 milliampere, and the value of this RD, okay, I think value of the RD we also need to find the operating point. Anyway, let me consider that RD is also say 3 k. And so, if this RD is equal to 3 k, then V out equals to VDD minus RD into IDS. So, that is equal to 12 volt minus RD, it is 3 k into 2 milliampere. So, that gives us 6 volt. So, the DC voltage here it is 6 volt. So, at the input, what you are getting here it is 3 volt DC here. So, this is 3 volt, I should say capital V small g s, and on the other hand at the output we are getting DC voltage, it is 6 volt. So, this is VDS, and then what is the value of the GM? Now, to calculate the GM, it is, so we obtain IDS, we obtain V out. Now, next thing is the GM. So, if you recall the expression of the GM, it is K W by L into VGS minus VTH, right. So, that is K is given as 1 milli. So, multiplied by VGS minus VTH. So, 1 into this is 2, 3 minus 1. So, 2 milliampere per volt. So, the GM it is 2 milliampere per volt. So, the gain, voltage gain AV, so that gives us AV equals to minus GM, which is 2 milliampere per volt, multiplied by this RD, which is 3 kilo ohm. So, that gives us a gain of only minus 6. Of course, this is a poor gain, but whatever it is, we assume that for the time being, let us assume that that is what we are looking for, and that may be sufficient. And so, at the input, if we are giving say sinusoidal signal, at the output, so we are expecting that corresponding effect coming here. So, let us try to see what is the corresponding signal swing we can get, or maximum swing we can get. Note that at the input we are giving a signal which is say 1/6 of this signal, and for the time being if I say that the output or this VDS variation is much more than whatever the variation we do have at the gate, and we do have the 6 volt here and we do have the 3 volt here. So, while it will be going to the valley, of course, this may be going to the peak here, and if I ignore this variation compared to this much of variation, then the gate voltage, DC gate voltage, it is 6 volt, and gate voltage drain voltage DC it is 6 volt, and then gate voltage it is close to 3. So, the minimum possible drain voltage we can say that 3 volt minus 1 volt. So, the valley here it can be as low as 2 volt if I ignore this variation, and then the corresponding signal swing from 6 volt to reach to this 2 volt, it is 4 volt, 6 minus 2 volt. So, that is what you can say that the output swing it can be as high as 4 volt. But in case if we are also considering this variation, you need to consider the gate voltage going slightly above, and based on the magnitude of this gain, you can say that if this is 4 volt, the corresponding variation here it is 4 divided by 6. So, then of course, the device it is just entering into the saturation. Anyway, approximately we can ignore that part, and then we can say that the output swing, in addition to this, the output swing output swing it is plus minus, at least lower side we are saying that this is 4 volt. Positive side, of course, it is not having any problem, it can go higher. And to get this maximum swing, of course, the required voltage at the input it will be and this plus minus 4 volt divided by 6. I think that is what I like to cover. And so, let us see what are the things we have covered in today's module. Yes, so basically today's primary discussion it was common source amplifier. So, we started with the operation of the circuit, and then now we have talked about the biasing of the common source amplifier. Since the gate voltage gate node is having 0 current, we can say that it must be through voltage bias, and then along with the voltage bias which is it is getting obtained by potential divider R1 R2 from the VDD, we need to consider signal coupling capacitors at the input port and output port. And then we have discussed about the DC operating point analysis. So, we have basically the MOS transistor, it has been replaced by equivalent circuit, which it is representing the equation IDS in terms of VGS. And then we have seen the small signal equivalent circuit, where the transistor it was replaced by GM into VGS, small signal VGS, and then we got the expression of the output gain. Then the small signal equivalent circuit, after dropping the DC part, we have mapped the amplifier into voltage amplifier, where the input signal it was voltage and then output also was voltage. The other possibility of mapping the amplifier common source amplifier into is transconductance amplifier, and there the input remains voltage and then output it was in the form of current. And in the transconductance what you have seen is that transconductance of the amplifier it is incidentally same as transconductance of this MOS transistor in this case. And then we have discussed about numerical examples where different biasing arrangements and it was given, and then what we have seen is that the voltage gain it is quite low, magnitude wise it was we obtained for this numerical example it was only 6. The output swing on the other hand, so output swing we obtained it was plus minus 4 volt approximately. So, probably for 12 volt supply output swing it is I should say it is lower. Now, if I compare this numerical example of this common source amplifier with the common emitter amplifier performance, you may recall that for common emitter amplifier the voltage gain it was much higher in the range of 200. So, definitely this is higher than this 6, and also the output swing in the common emitter amplifier it was in the range of plus minus 6 volt. So, close to plus minus 6 volt. So, we can say that performance wise common emitter amplifier it is better than the common source amplifier. So, both the gain wise and the output swing wise. Then the natural question is then why do we go for common source amplifier? The answer is that whenever we will be going into microelectronics and VLSI, VLSI design, where MOSFET transistors are the primary elements, and to realize this amplifier, voltage amplifier, we need to use MOS transistor rather than BJT. So, I should say that whatever the technology will be it will be available to us, and if we integrate analog and digital circuit together, then it is better to explore this common source amplifier. And in case if we are not happy with this, particularly the gain part, maybe we can try to use some other alternative, namely instead of using say passive load, we need to consider active load. So, instead of RD, we can use probably active device here or active load. So, in case if we are successfully replacing this one, there is a possibility of improving this gain, and practically that is what it is done. So, probably we will see that down the line whenever the situation permits, we will replace this passive load by active load. The other information I like to capture here, it is that particularly in the context of microelectronics and VLSI design situation, in this numerical example, in today's numerical example, we have considered that K into W by L, it is given to us. This is the case whenever we are doing the board level design. We assume that this not only this parameter, but also aspect ratio of the channel of the device is given to us. But when you consider VLSI design, the additional flexibility is that the designer can decide what will be W and L. So, in the analog VLSI design, W and L will not be given, rather it will be the freedom, it will be given to the designer, and the designer of course have to make a meaningful selection of W and L to further optimize the performance of the circuit. So, whenever we will be going for advanced level subject such as analog VLSI design, then we will be dealing with variation of the W and L, or rather how do you select W and L of the devices. But in this subject, in analog electronics, we assume that this entire quantity, namely K into W by L, is given to us, and then we proceed for design, namely selecting the different bias components and then the load. I think that is what we like to cover. Thank you for listening.